Dear students, after studying this module, you shall be able to know the axis chirality in allenes, that is the axial chirality in allenes. You shall also be able to know the structure and point group that exist in allenes. You should also be able to distinguish between asymmetric and dissymmetric allenes. This module shall also help you in determining the absolute configuration from the structure, also help you in the analysis of various methods of the synthesis of allenes and identify the enantiomers of the allenes. Now let us begin with a slight introduction of the allenes. Certain stereoisomers which do not possess the center of chirality, that is the stereoisomers of allenes, atropisomers of biphenyls and ANSA compounds, but they are chiral. And two additional stereogenic units are introduced, they were introduced in 1956, that is the chirality plane and the chirality axis. So these are the planes, chirality plane and chirality axis, due to which the allenes or the biphenyls or the ANSA compounds are treated as chiral compounds. As early as in 1875, Van 't Hoff pointed out that an appropriately substituted allene should exist in enantiomeric forms. So what is a chirality axis, students? An axis about which a set of substituents is held in a spatial arrangement that is not superimposable to its mirror image is created or is known as the chirality axis. The simple principles for the chirality axis and the chirality plane have recently been refined by Prelog and Helmchen in 1982 as elongated or extended tetrahedral approach to this particular problem. So what is the elongated tetrahedral approach to this? A regular tetrahedron with 4 distinguishable vertices, that is structure A in this figure, presents a 3-dimensional chiral complex or simplex. The central tetrahedron, which is usually occupied by the tetra coordinate atoms, that is carbon in C ABCD format, if this center is replaced by a linear grouping such as CC bond or C double bond C, that is the allene, the tetrahedral becomes elongated along the axis of the as shown in B figure. In allene, now it becomes as ABC double bond with the 2 double bonds existing and C in the center, which is sp hybridized, then again the last carbon which is attached to AB again. Such elongated tetrahedron possessing the D to D point group with 3 C2 axes and 2 sigma planes has lesser symmetry than a regular tetrahedral possessing a TD symmetry, and condition for desymmetrization is less stringent. Instead of all the 4 vertices that should remain distinguishable. In the case of allene of only pair of vertices of 2 ends of the axis, they need to be distinguishable, that is A should not be same as B. The axis along with the tetrahedral is elongated, is also called the chiral axis or the stereo axis. So what are the types of allenes known to us? First is the asymmetric allenes. Allenes having an asymmetric carbon or C1 point group are classified as asymmetric allenes. Other ones are, the second one is the dissymmetric allenes. Allenes having C2 point group are known as dissymmetric allenes. Structure and hybridization in allenes. Now we shall study this topic. So what are the structural details of allenes? Hybridization in allenes for central carbon is sp and the 2 terminal or the carbons at the edge are sp2 and exit as trigonal. The hybridization of central sp hybrid carbon atom must use 2 different p orbitals to form a pi bond with the 2 edge carbon atoms. If these 2 pi bonds are perpendicular to each other, as shown here to you can see here that the pi bonds are perpendicular to each other, and you can see the pi bond or the p bond overlapping in allenes. Now we shall study the point group symmetry in allenes. We have learned that allene has 2 pi bonds perpendicular to each other. It has 3 C2 axes, that is one which passes through 3 carbon atoms of the allene, the other which passes through central carbon of allene, and the third one which passes through the central carbon of allene perpendicular to the earlier axis. It is shown clearly in the figure. It has one improper axis of symmetry, that is S4. It passes through 3 carbons of the allene and plane is perpendicular to this. The rotation of 90 degrees and then reflection through the plane gives indistinguishable allenes, so thus they exist as chiral molecules. It also contains 2 sigma planes, that is the dihedral planes, as shown to you here in the next figure. The point group thus of allene is D2D. So what are the conditions for chirality in allenes? Allenes, also called as 1,2-propadiene, has a point group of D2D as explained. Itself is achiral because it has 2 planes of symmetry. It could be chiral if the plane of symmetry is eliminated by the substitution of the terminal carbon atoms by different groups. That is, if hydrogen is replaced by a methyl group, as shown here in the figure. An allene with substituents on one terminal carbon atom are unlike and the substituent on other terminal carbon atoms are same. Allenes will be achiral. It will have only one symmetry plane. The cumulene with odd number of double bonds with terminal carbon atoms having unlike substituents also will be achiral because both terminal planes will be same, as shown to you here in the figure, which is clear that it is an achiral allene. Now let us discuss something about allenes occurring in natural products. Allenes are interesting molecules and this core structure was found in many natural products. We have shown some structure where allene is core unit in natural products, which is shown here in figure. We have shown some core structures. You can see here the basic core structure contains allenes. First naturally occurring allene was pyrithrolone and it was characterized by Schrödinger and Ruzicka. This is reported in almost as back as 1924 in Helvetica Chemica Acta. Now you can see here there are various molecules here which are natural products. Some are insect pheromones and some are grasshopper ketones, and they all contain allenes as the core products or the core molecules. Synthesis. Now we shall discuss the synthesis of optically active allenes. Nowadays about 150 natural products comprising an allenic or cumulinic structure are known. The chemistry of these compounds has turned out to be a very attractive and prolific area of interest. Advances in the isolation and characterization of new allenic natural bonds have led to the establishment of efficient synthetic procedures, which in many cases also open up an access to enantiomerically pure target molecules. So now we would like to discuss some methods of synthesis of allenes. First one would be, students, the dehydration of allylic alcohols. The first optically active allene was prepared by Maitland and Mills in 1935, 60 years after Van 't Hoff's prediction. 1,3-diphenyl 1,3-dialpha-naphthyl 2-propene-1-ol was dehydrated with plus and minus camphor 10-sulfonic acid respectively. With plus minus camphor, that is, if I am referring to as plus minus, that means that they are the rotations observed in the polarimeter. Camphor 10-sulfonic acid, the allene was obtained as racemic, while the plus sulfonic acid, slight enantiomeric excess, that is 3%, was obtained. Now this is shown here clearly in this figure, in the synthesis of optically active allenes. The second method is the kinetic resolution of chiral allenes. The optically active allene was synthesized by kinetic resolution of racemic compounds. Racemic compound is a mixture of equimolar amounts of, that is 50-50% of enantiomers. In the kinetic resolution, one enantiomer reacts faster than the other enantiomer. One enantiomer reacts fast and gives the product, and the slow reactive enantiomer will be as it is in the reaction mixture. The kinetic resolution of racemic allene with chiral hydroboration agent IPC2BH gives the optical reduction product as borane compound, and optically active allene was found to be unreacted during the kinetic resolution process. Now you can see here how we can separate the optically active allene by kinetic resolution of the racemic allene Third is the reductive rearrangement of chiral acetinic carbinol to obtain the optically active allene. In the synthesis, the ether of optically active acetylenic carbinol is treated with LiAlH4, that is lithium aluminium hydride, which is a reductive agent which gives the enantioselective allene. The addition of hydride is trans and the hydride approaches to acetylene from the opposite sides of the OTHP leaving group. Now you can see here how the reductive rearrangement is being performed in this scheme 3. Fourth method is the ortho ester Claisen rearrangement. In as early as 1988, Mori et al. Prepared the enantioselective allenes for the synthesis of the sex pheromones produced by male dried bean beetle. Now you can see here the production of this pheromone as shown here in this figure showing the ortho ester Claisen rearrangement. Now next question after this synthesis and after knowing how the enantiomers of the allenes can be formed, now next question is how to assign the RNS nomenclature of the allenes. If we view the molecule from the left hand side as you can see here and change it to the Newman projection, and according to the priority rules given by the CIP, that is the Kahn-Ingold-Prelog rules, we can set the 1, 2, 3 in the Newman projection and then we can see the clockwise or the anti-clockwise rotation in this particular allene which is shown to you. Now if you see here, after putting it in the Newman projection and after seeing the rotation whether it is anti-clockwise or clockwise, it turns out that it is a clockwise rotation. Thus this particular allene is showing having the R configuration, R as the absolute configuration. Now when you view this same allene from the right hand side, then also you can see putting it in the Newman projection, again the rotation comes out to be R and thus the absolute configuration of this allene comes out to be R, whether it is from the left hand side view or the right hand side view. Now we shall learn about the representation of enantiomers of the allenes. The enantiomer of allenes can be represented in the mirror image of the allenes is shown in this figure as seen here. The compound 1 and its enantiomers can be written if one terminal carbon atom substituent is interchanged. Compound 1, that is the right terminal carbon atom substituents interchanging with its enantiomer 2, and if compound 1 in this the left carbon atom substituent interchanging with its enantiomers gives us enantiomer number 3. Now you can see here how by interchanging you can have different types of enantiomers and you can put it in the correct amount of representation for the allenes. And you can see the mirror image of allenes by the representation here also. These 3 compounds are written above. Their enantiomers are identified by giving the absolute configuration according to viewing through different axes, that is the left hand side axis or the right hand side axis, and then putting it into the appropriate Newman projection and seeing the absolute configuration. Now you can see here according to this the configuration of the present allene is the S because it is having the anti-clockwise rotation from both the angles. And you can see here another R enantiomer is also there. By putting the same, by viewing it from the left hand side, we have put it into the Newman projection and then you can see here that we are obtaining the R enantiomer because of the clockwise rotation. Again here you can see with the third allene, you are having with the third enantiomer of the allene, we can see that it is having the R configuration as the absolute configuration. Now students, after having studied so much about allenes, their structures, their synthesis and their absolute configuration and their representation of enantiomers, I would like to summarize this module. This module will give you the understanding of stereoisomerism of allenes as we have already taught you, and we have also given you the 3-dimensional structure of the allene. Allenes are the examples of axial chirality. Allene's central carbon is sp hybridized and the terminal carbon atoms are sp2 hybridized. Allene moiety also exists in many natural products and there are various ways of synthesizing allenes. That includes dehydration and rearrangement and also ortho Claisen rearrangement. And also we have taught you various ways of representing the enantiomers of allenes and how to actually assign the absolute configuration in various enantiomerically active or the chiral allenes.